Howdy, math peeps. So, we are talking about trigonometric ratios. Okay, and before I get really into what that is, let's kind of look back at what we've done so far. So, in 9.1, when we were solving things for triangles, we had something like, okay, it's not beautiful, but it's fine. So, if we had a triangle and we knew two of the sides, could we find the third side? Well, this is a Pythagorean triple, right? 3, 4, 5. So I know the third side would have to be 5. So given two sides, we're able to find another side using the Pythagorean theorem, right? Even if we didn't know that this was a triple, you could do 3 squared plus 4 squared equals c squared, and you would still get that that's 5. And then in the other section, so this was when we were talking about 9.2, we used special right triangles. So if we were given information, like for example that this was an isosceles right triangle, then that means we know that this would be a 45, 45, 90 triangle. So if this side were, if we were given that that side were 7, then we could follow the patterns, because if it's one of the special right triangles, we know some things about side lengths. So we could follow patterns to get that this other side is 7, and then that this one here is 7 root 2. And we could still do Pythagorean theorem to get there, but this is much faster. And then the other kind of special right triangle we had was the ones that were 30 and 60. So if this one's 60 degrees, then we know that if we were given, say, the shorter leg, 5, so this we could have used Pythagorean theorem on. If this is all we had, we can't use Pythagorean theorem, but we can get the rest of these with our shortcuts. So remember, hypotenuse here is 2 times the short leg, so this would be 10, and the longer leg here is the short leg times root 3. So that would be 5 root 3. So hopefully you understood those two things pretty well. So now what would happen, though, if we had a triangle that didn't exactly fit into one of those categories? So, say for example, if I had one side, and I know, like, an angle, so if I had something like this here, so if I know that one side's 5, and an angle is 10 degrees, how could you figure out another side here? Or, and if this one were one of the special ones, right, like a 45, 30, or 60, we would know what to do. But if it's not, so far we don't know what to do with that. Or if you had a different one where it was like, this is 75 degrees, and this is 17, something like that. So these are the kinds of problems that we'll get to do today, and you're going to be using trig ratios to solve for the missing sides. So, if we were doing this in class, I would have had you do this kind of activity here. So this is just what it looks like. I went ahead and did it. So given a 40-degree angle you start with, so we label the sides with respect to this 40-degree angle. So this one's the side opposite of it. Hypotenuse is always the hypotenuse. Adjacent is the one next to it. And then I just drew a thing here, a triangle with whatever length I wanted. It just had to be a right triangle with this angle. And I measured the sides and then divided opposite side by hypotenuse length, got about 646. So what we would have seen is that regardless of what you chose your side lengths to be, we all would have gotten basically the same thing when we divided these ratios. So because of the way that triangles work, especially with right triangles, they have the same ratio for a specific angle with opposite, adjacent, over hypotenuse. So we're going to talk about specifically what those are, but if you were to take, say, so if you see in your calculator, you remember, you may have seen those buttons before, the sin, cos, and tan, these ones right here. So these are what those trig ratios are. So if you were to take your calculator and do sine, is what we call it, of 40, you would get this opposite over hypotenuse ratio. So it's the same for the same angle, regardless of what your sides are. So let's take a look at this a little bit further. So this is how it looks with what your book would say. So defining sine, cosine, and tangent ratios. So ABC here is a right triangle with acute angle A. And sine of A is the length of the leg opposite A divided by the length of the hypotenuse, or BC over AB. Cosine, length of the leg adjacent to A, length of hypotenuse, and so on. So usually the way we'll actually see this written, to make it a little bit less cumbersome, is, and actually I do want to point this out here, so these are sine, cosine, and tangent. So they are abbreviated SIN, COS, and TAN, but even though we only write them with the first three letters, we still say the full word. So don't say sin, cos, and tan. You're not going to sound educated. So, yeah, we say their full name even though we abbreviate them. The other thing I want to emphasize is that it's of an angle. It's a function of an angle. So it doesn't make sense to say, like, sine equals something. No. It's sine of an angle. That'd be like saying square root equals, well, square root of what? So it's always a function of an angle. So just keep that in mind there. So the sine of an angle, usually the way we'll write this, it's a little bit shorter, is it is the opposite over the hypotenuse. And then cosine of an angle is the adjacent side divided by the hypotenuse. And tangent of an angle is the opposite side divided by the adjacent side. And you may have heard or seen SOHCAHTOA is a thing that people talk about. It's a way to help remember these ratios. So it's so, because its sine is opposite over hypotenuse, ka, toa. So it's a way to remember sine of the angle is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And a different way I'd heard to remember this from a different teacher, it's kind of funny, is some old hippie caught another hippie tripping on acid. So if that's an easier way for you to remember it, go for it. Most people just use SOHCAHTOA, that's the one I use. So let's look at how that works with an example here. So we're going to use this triangle. Now, we are going to look at finding, we'll start with angle B here. So when we're talking about opposite, adjacent, all of that, it's with respect to a certain angle. So if I wanted to find the sine of B, so it should be opposite over hypotenuse, but we need to label our sides with respect to B, from B's standpoint. So it's like if I'm standing here chilling at B and looking at these different parts, so the hypotenuse is always the hypotenuse, so that's easy enough. And then right across from the right angle, longest side, hypotenuse. Then opposite side would be the one across from that angle. And then adjacent side is the one that is touching the angle or making the angle with the hypotenuse. So sine of B would be opposite over hypotenuse, which for this triangle is the is AC over AB. And then cosine of B, it would be equal to the adjacent over the hypotenuse. So that would be the adjacent side BC, or CB, doesn't really matter, divided by the hypotenuse AB. And then finding the tangent of angle B, it's opposite over adjacent. So if I were looking for that, I would find the length of AC and divide it by the length of the adjacent side, BC. So that would be with respect to angle B. Now if I were to switch it up and instead say, looking at angle A here, so if I were to find the sine of A, then I need to evaluate where my things are. So hypotenuse is still the hypotenuse right here, but my opposite side is not the opposite side anymore now. This is the adjacent side to A. And then this one that was adjacent to B, this is the opposite side with respect to angle A. So the sine of angle A is still going to be opposite over hypotenuse, but that is going to be now BC over AB. And then cosine of A is going to be adjacent over hypotenuse, which is going to be AC over AB. Then tangent of tangent of A is just going to be opposite over adjacent, which this time is going to be BC over AC. So if you're looking at these here, you may notice, hopefully, that the sine of B here, this AC over AB, is the same as the cosine of the other angle. So those two are related. And then if you look at the sine and cosine in this direction, so cosine of B is BC over AB, and that's also what the sine of A is. So those two are also related to each other, and in fact are the exact same thing. The tangents aren't the exact same, but they are like flipped of each other. So if you were to flip the tangent of B over, that would be the tangent of A. Right, so just remember these are called trig ratios because they are ratios of different sides in a right triangle. So let's look at this next little thing here. So sine and cosine of complementary angles. Now we noticed on the other slide just there that the sine and cosine of the two different angles ended up being the same. So this is telling us for a setup. So let A and B be complementary angles. So we have a right triangle here. So it's 90, and we'll call this C, A, and B. So it's telling us A and B are complementary. Which means what? Do you remember? Alright, so A and B, complementary angles, add up to 90 degrees. And in a right triangle here, the complementary angles, or excuse me, the two acute angles are always going to be complementary, right? Because it has to be 180 total. That 90 is already spoken for, so the other two have to add up to a total of 90. So in a right triangle, acute angles are always complementary. And the result from kind of what we saw before this one is that anytime you have a set of two complementary angles, the sine of one is equal to the cosine of the other. So the sine of A and this is equal to the cosine of B, and vice versa. Cosine of A would be equal to sine of B, and so on. So we can actually look at this in here. So if we wanted to write this, so sine of 9 would be equal to cosine of what? So you'd have to think about what angle is complementary with 9. Well, that should be 81. So the sine of 9 degrees would be equal to the cosine of 81 degrees. And then kind of same thing going the other way. So cosine of 83, well, it takes 7 degrees to get to 90, so that would be equal to sine of 7 degrees. Sine of 30 degrees, you'd think 30 from 90 would be 60, so that's cosine of 60 degrees. And then cosine of 45 degrees, so complementary, add up to 90, is sine. So the cosine and sine of 45 degrees are actually equal to the same thing. So that's where we're going to start, and now we're going to go ahead and look at how we actually find these ratios with numbers in place. Stay tuned.